In this section, we're going to solve rational equations. Most of the time when we're learning all these different algebraic simplifications and how to rewrite something, kind of our ultimate goal is to get to an equation which has an equal sign in it, which means we are able to solve for x and actually find out what x is, because in real life applications, x might represent something like miles or speed or whatever, and we need to find out what the missing letter is in any particular situation. So we're going to learn to solve for x using our LCDs, but using them in a similar way that we did in the complex fractions section, where we don't actually make all the denominators become that LCD, but we use the LCD to clear the fractions or clear those denominators. And so that's what we're going to do here. And let's first figure out what the lowest common denominator is. First thing you want to do is factor any denominators that can be factored, and this one is already done, so I rewrote it here. This one's done, so I rewrote it here. And this one was a difference of squares pattern, so I factored it underneath and I rewrote it here. So we've got my three denominators, and again, you want to circle any that they have in common because you only need to write those once. You don't have to write them multiple times, and we have those in common. So our LCD is an x plus 1 and an x minus 1. We need both of those. So instead of making these denominators become x plus 1, x minus 1, we're going to use the LCD for a different reason. We're going to use it to clear the denominators, because you can always take an equation, multiply both sides by the LCD, and you'll actually have no more fractions, which is great if we can get rid of fractions first thing. So that's what our goal is to take the LCD, multiply it through on both sides of the equation, and get rid of our fractions. So I'm going to do that on the next page. So what your goal is to multiply both sides of the equation by the LCD, but while you're doing that, you're going to distribute it to both of these terms. So basically, you're going to multiply the LCD by every single term. And so what we want to do is write it here, which it was x plus 1, x minus 1. That was the LCD. And then an x plus 1, x minus 1 here, and then an x plus 1 and an x minus 1 here. And notice I rewrote that denominator in its factored form so we can easily see what factors will cancel. So on the first fraction, which we have right here, we're going to cross off this with this, and we're left with the other factors, and then we cross off this out of this denominator, in this fraction, we cross off the x minus 1 with the other x minus 1. And on this one, you can cross off two matching factors. And so let's write what we have left in each of the three sections of this problem. So this is what we had left over, and the nice thing is this is much easier to work with than the original problem. So the goal is take the LCD, multiply it by everything, and as long as you're doing it to both sides of the equal sign, you don't have to do it top and bottom. You can just do it to both sides of the equal sign, left and right, and that makes it legal. And so we are going to cancel out all the denominators and put what's left, and this is what we have. So this is an equation that we know how to solve. So first we're going to distribute, and then we're going to see what we get. This is what I got when I distributed, and I'm able to combine some like terms here, and actually these two just undo each other and make a 0. So I end up with 2x squared equals 2. And so I'll divide both sides by 2, and I get x squared equals 1. And don't forget, when you square root both sides, you have to write that little plus or minus, and therefore you get plus or minus, the square root of 1 is 1, and you get two potential answers. But these are the kind of problems where you always need to check to see if those answers actually work in the original problem. And especially if it was to make any of the denominators 0 along the way. If it made any of the denominators 0 along the way, that would make that fraction undefined, which is impossible. So we want to see if first, maybe just check to see if it makes any of the denominators 0, and then if that checks out, test it in the entire problem to see if the left side equals the right side. Okay, so what we need to do is go back to the original equation. You can see my screenshot there. And then we're testing to see if x equals 1 works, and we're testing to see if x equals -1 works. So what I did was the first time through I plugged in a 1 every time I saw an x. The second time through I plugged in a -1 every time I saw an x. And you can see that right here 1 minus 1 makes a 0 on the bottom of a fraction. So that immediately just shuts out that whole answer because you can't have a 0 on the bottom of the fraction. It also makes a 0 here because 1 squared minus 1 is also 0. But if it makes a 0 on the bottom of any fraction, you're done with that answer. So 1 cannot be an answer. Same thing on -1. It turns out that this denominator becomes 0 and this denominator becomes 0. And so it makes those fractions undefined, so we have to scratch this answer as well. And unfortunately, this whole problem, after all that work, gives us no solution. But we'll have a lot of problems that won't give us no solution. Maybe one will work and one won't work, or maybe you'll have them both work. It just depends on the situation. So let's try another example. This example is very similar to the other example. Almost everything's the same and even the same type of pattern. This is a difference of squares pattern. So it matches the other denominators, and so we know that the LCD is going to actually be the x minus 3, x plus 3. Again, refer back to the last example to see why that's true. So what we're going to do is we're going to multiply each fraction. We're really just multiplying both sides by x minus 3, x plus 3. But while we're doing that, I'm going to go ahead and distribute it to each one so that we can individually cancel each fraction as needed. So what we have is this denominator cancels with that numerator, this denominator cancels with that numerator, this factor cancels with this factor cancels with this factor, and let's put what we have left. Okay, in blue we have what's left, and that's a very similar scenario to the other one where we need to distribute, combine like terms, and see what we have to work with. And again, after we distribute, we see that these like terms cancel each other out. We have 2 of the same, so we have 2x squared equals 2. We have x squared equals 1 when we divide by 2 on both sides. And then we know from the last example that that'll give us both a plus or a minus 1. So the only difference is when we plug it back in, it may work this time because you can see that putting a 1 here or here is not going to cause a 0, which is a good thing. But that doesn't necessarily mean both answers work, but we need to at least try them and see if the left side ends up equaling the right side. Okay, so here's the original equation. The first time through I put a 1 in for all the x's, the second time through I put a -1 in for all the x's. So let's check to see what we have. So this is what we have on each fraction, and if you put these two together, you get -1/4, and if you reduce this, you get -1/4. So since those equal each other, our answer of 1 checks out. And then we'll look at this one. We have a +1/4 and a -1/2. Which equals -1/4. And then we have a -1/4 on that side. So since the two sides equal each other, we can say that -1 is also an answer. It checks out. So both -1 and 1 are answers this time. So don't just always assume that it does or doesn't work. You need to really plug it in, and sometimes you'll even have one work and one not work. So that is how you check to see what your solutions are. So the answer to the question is that x equals both positive and -1 in this particular problem. A very common application problem that is related to these rational equations is something about an airplane flying into a headwind or being pushed from behind by a tailwind, or oftentimes I see this as a boat problem where it's going upstream or downstream, so the current is pushing against it when it's going upstream, and the current is pushing from behind when you're going downstream and making it go faster. So either one of these situations will be an example like this. This is an example from the Pearson Algebra 2 Common Core textbook, and it says a flight across the U.S. takes longer east to west than it does west to east. And the reason is that winds are constantly pushing in the eastward direction. So when flying westward, the headwind decreases the plane's speed because it's pushing against the front of the plane. And when flying eastward, the tailwind increases its speed because it's pushing against the tail, so it's making it go faster. The time for a round trip is 7 3/4 hours. If the airplane cruises at 480 miles per hour, what is the speed of the wind? And this is, the 480 is what the plane's engine is set to. But that may not be the actual speed they're going as compared to the ground, because the wind is actually pushing them a little slower or faster than that. But the speedometer or whatever is set to 480 degrees cruise control. So, I mean miles per hour, not degrees. So we want to know what is the speed of the wind. And so we're going to let wind be, or the speed of the wind be W. And the other formula we need for these is that distance equals rate times time. And that is a very common formula, distance equals rate times time, rate being the speed. So let's put these things together in a little chart so that we can see what we have to work with. Okay, so here's a chart you could set up that kind of has all the pieces that we need. The direction the plane is heading is either west or east, which means west he's going in to the headwind, and east he's being pushed by the tailwind. And we need to compare these two, and we've got rate times time equals distance. I always like to put the equals piece at the end, and so I switch the formula around. And let's put in what we know from the problem. We can see from the picture that each direction is an 1,850 mile flight, and so both the west trip and the east trip will take 1,850 each. So I'll put that in the distance spot. The rate is affected by the wind, so we can't just put 480. What we have to do is put 480, and then when you're going into a headwind, you're being slowed down by the wind, so the wind speed that's pushing against the plane will actually slow down the plane by that much. And then the tailwind, actually the wind is coming from the back pushing the plane faster, so however much the speed of the wind is going to make the plane go that much faster, so we want to add to the speed. And then T, we want to make that a combination of the other two pieces, because we don't want to split the 7 3/4 hours half and half, because it's not going to work like that, because one's going to be faster than the other, but we don't know how that ratio works. And we don't want to introduce another variable. So what we're going to do is make T a ratio of the D and the R. And so if you think about solving for T, we would divide both sides by R. And so we would get that T could equal D over R. And so we're going to put the distance over the rate and write that as our time. Then once we write our time in, what we know about the time is that it has to total 7 hours and 3/4 of an hour additional. So we're going to take these two times, add them together, and say they have to equal 7.75 hours. And so that's what we're going to do on the next page. So we have the time of the headwind trip, the time of the tailwind trip equals the total time of the round trip. And so we work all this out. You can copy these steps down in a minute, but we get that W equals positive or negative 35. Negative speed doesn't make a lot of sense in this problem, so the wind speed is 35 miles per hour, the positive version.